Welcome to Maths with Bob. Today we're looking at vectors, or a vector application, I guess you could say. It's to find the distance of a point in three-dimensional space to a plane with an equation ax plus by plus cz equals d. Okay, now what do we want? Well, the first thing, let's have a quick look what we want. We obviously bring this arrow in. You can see here we want this. Okay, this is there's a bit here from P to R. Okay, that's the perpendicular distance of P from the plane, this grey section here. Now, we're going to let D represent this perpendicular distance. So it's D. D is actually equal to PR, you can see here. Now, how do we go about doing this? Well, first of all, from the equation of the plane, we need to get the normal. You might remember the normal was actually the dot product or to find the equation of a plane, we use the dot product of a free vector and the normal. Okay, and basically they were actually perpendicular, so the dot product was equal to 0, and you generated the equation of the plane. But to start with, R here, okay, oops. R is actually, you can see here, a point on the plane, but we don't actually need R. We don't really need, well, we don't really know where R is. Okay, but we do have to generate a point Q on the plane, Q over here. So we are going to have to basically generate a point on the plane. Now, okay, we'll do this in a minute, but basically you just try and select some nice values which satisfy the equation of the plane. Okay. All right, okay, so here we have the equation of the plane, ax plus by plus c equals d. Sometimes you can put the d on the other side, and you'll see later on when I derive the equation of the distance formula for the coordinate geometry formula, if you like, of the distance of the point P from the plane. You'll see I actually put the d on the ax plus by plus c plus d equals 0 just to help us derive the formula. But basically from the plane's equation, you can see here, straight away you can just pick off the a, b and the c. Okay, ai plus bj plus ck. This is the equation of the normal. Now, okay, so the normal, this is the normal. Now, hopefully, if you haven't watched the video on points and planes, it's probably not a bad one to have a look at too. But basically, this is used to generate the equation of the plane. So it's easy. Well, once you have the plane, you can quite backtrack and get the normal quite nicely. Okay, now with the normal, we have to normalize it. Now, normalize. Okay, what does normalize mean? Well, normalize just means you create a unit vector from the normal. You divide it by its length. That's another fancy way of saying, I suppose, just get the vector and divide it by its length. Okay, that normalizes the big N and makes a little n. N is actually a unit vector. Okay, in the direction of the normal. Okay, now, okay, so we've got to generate this free vector as well, Q from the point Q. So we needed that point Q. Okay. And we generate this vector PQ, okay, and then you can see here that if I look, it's like a bit like a projection, I guess you could say, that vector onto this normal here. If the normal is coming up this way, it's like a bit of a projection, if you like, onto the normal's direction. Okay, but because of the dot product, you'll see later on that if we do a PQ dot, this little n here, n is length, we'll actually get what's called PQ cos theta. Now, PQ cos theta basically is in fact the distance d, which is PR, which is what we're after. Okay, so the normal vector can be constructed quite easily from the components. Okay, you can see of the plane. We normalize the vector, divide the normal by its length. Okay, which gets the unit normal vector. Okay, and then we basically have to do a bit of a dot product, and we actually take the absolute value, okay, of this, so we don't want it to be negative. Okay, so hopefully we'll go through an example. We'll have a look at this a bit more detail. Okay, so you may have forgotten what the dot product is. Well, okay, the dot product, okay, of two vectors, okay, you can see here, it is a scalar, and hopefully you remember it's just a number. Okay, you can see here, this is the dot product. It's just a dot b is, okay, the length of a, or the magnitude of a, times the magnitude of b times the cosine of the angle in between. Okay, and you might remember the cross product was the sine. Okay, But anyway, and the answer was a vector as opposed to a scalar, which is just a number. Okay. So what do we do? Well, okay, here we go. PQ.n. Okay, now PQ.n is basically the length of PQ. Okay, so you're just following along here. The length of n, which we know is 1, is a unit vector, and times the cosine of the angle, okay, between the vectors. And you can see here, this is basically PQ cos theta, which is PR. Okay, so PR is D, which is what we're after. Okay, D is P. Okay, so, all right. Now, okay, so you can see here, this free vector needs to be, well, needs the point, obviously, and it generates something like this. Okay, this is the equation of the free vector from P, okay, to Q, okay, coming down this way, P to Q, and you can see here you start at Q, so it's x0 minus x1i, and then y0 minus y1j, and then z0 minus z1k. Okay, so this is going to be the free vector. This is going to be handy because when we actually do the dot product, we'll actually generate, if you like, the perpendicular distance formula in 3 dimensions, actually, with this aid of this vector PQ here. Okay, let's look at an example now. Okay, here we have an example, and we're going to just look at, we can see here, it's pretty easy. How far is the point? Minus 1, or sorry, minus 2, 5, minus 3. To the plane 3x minus 2y plus 4z equals 5. Okay, so I just made up a point and a plane. Okay, you can see straight away the normal. Okay, we're the normal here. Okay, now, as I said, it's very easy to pick this normal up. Okay, you can see here the 3, the minus 2, and the 4. Okay, quite easily regenerated from the equation of the plane. Obviously, we don't use the 5 here at this stage. Now, okay, so we now have to find Q. Okay, so you may have to fiddle with the numbers, as I said here, but if I let x equal 1 and y equal 3, okay, and I sublet those numbers into the equation of the plane, okay, 3 times 1 is 3, minus 2 times 3 is minus 6, okay, that's, what's that, minus 3, put it on the other side, 8, 4z's 8, z's 2, okay, so we now have a nice plane, point on the plane, if you like, q, 1, 3, 2. Okay, so we then now generate PQ. Okay, now PQ. Notice P's up here and now Q's here. So it's 1 minus minus 2, which is 3i. Okay, 3 minus 5. Okay, minus 2j. And then 2 minus minus 3, 5. Okay, 5k. So here we have PQ. Okay, so this is what basically this is our free vector. Okay, now we need this, obviously, because we're going to dot it, you can see shortly, with the normal. But before we can do that, you'll have a quick look here. We need to what's called normalize the vector n to get little n. Okay, so capital N is the normal vector, and we just divide it by its length, which is actually root 29. Okay, you might remember it's the square root of 3 squared plus minus 2 squared plus 4 squared. Okay, to get the square root 29. Okay, so once we've done that, we then just do the dot product. Okay, the dot product you can see here. And how do we do the dot product? Well, we just multiply corresponding components, like 3 over root 29 times the corresponding component of PQ. Now PQ's corresponding is 3, so it's 3 times 3 over root 29, and then obviously minus 2 times minus 2 over root 29, and then 5 times obviously 4 over root 29. Okay, to get a length of basically about 6.128, approximately 33 over root 29, the exact length PR, which is D. We're going to let it equal D. Okay, you can see here the plane over here, which we obviously use to get the normal. Okay. Okay, now if we generalize this result, I'm going to now just derive the formula. Basically, this is the distance formula, which is this one over here. Okay. This is this one, which we'll come back to in a minute. But basically, this is a quick and easy way. I mean, the coordinate geometry way of doing this is quite difficult, but you can see here the vector technique is really quite easy, actually. So first up, we say we want a point P, obviously, which is going to fire a normal vector towards the basically the plane and try and measure its distance, I guess, from this point. Okay. We notice we don't find out where the line or the normal would intersect with the plane, so we don't need that. We're just doing like a projection, if you like. So this is x1, y1, z1, which is the coordinates of P, and you can see here I've written the plane as ax plus by plus cz plus d equals 0, just to basically just to help us out with the to get the signs correct, if you like, for the formula down here. Okay, so you can do this a couple of ways, reverse the directions of the vectors if you like, sometimes that helps us. But if we just want to follow through this one, okay, so this is quite an easy way of doing it. So the first thing is, okay, so here comes our vector, a free vector again, PQ. Okay, now this, you might remember, this was to some point Q, x0, y0, z0 on the plane. Okay, you do need to have that, and obviously P is just x1, y1, z1. Okay, so that's a free vector. Okay, again, you can see here, well, the normal, we'll just let the normal be generalized here to, you can see here, where's the normal? Okay, ai plus bj plus ck, and then obviously we just normalize it, we have to divide it by the square root of a squared plus b squared plus c squared. Okay, so to get little n, the unit vector, unit normal vector. Okay, then we do the dot product. Now the dot product again, as you can see here, is just corresponding components multiplied together. So it's basically, what is it? Here we are, x0 minus x1, x0 is x1 times a over the square root of a squared plus b squared plus c squared. Okay, so this is this bit here. Then you do it y0 minus y1 times the corresponding component b over the square root of a squared plus b squared plus c squared, etc. Okay, so you end up getting this formula here. You multiply it out. Now, you do need to put the point into the plane, so you do know that ax plus by plus cz plus d equals 0, and if you put in x0, y0, z0, okay, the point on the plane, which is q, you can see here that that's equal to d. I moved these terms across the other side, basically because when I expand this out, I'm going to get you can see here, an ax0, by0, and a cz0. That would give me positive d, but well, that would give me, what would that give me? Okay, that would give me negative d. Yes, I suppose you can just see it's negative d, so I could put that straight into here, I guess, if you wanted to. But I've just rearranged this thing here to show you that, in fact, when I multiply that out, a x0, by0 plus cz0, I'll actually get the negative of d. And we take the absolute value, you can see here, basically of the top here, and well, this will be the absolute value of negative 1 times the absolute value of a x1 plus by1 plus cz1 plus d over the square root of a squared plus b squared plus c squared. And obviously, you know, the absolute value of negative 1 is just 1. So you can see here, this is the formula here, basically. Okay, and you can see over here, this is really quite a nifty little formula here. Okay, this is the formula down here. D is equal to, okay, the absolute value of ax1 plus by1 plus cz1 plus d, okay, its absolute value basically divided by the square root of a squared plus b squared plus c squared, okay, which is basically the length of the normal. Okay, so let's just check the formula. I put the numbers back in here to show you that it does work as before, so you might like to go through that for yourselves and have a quick look at basically how it worked. Okay, so we just use the pointer x1, y1, z1. Okay, you can see here, and we use the a, b, c, and d from the plane. Okay, and then obviously we divide it by the square root of, okay, this thing here, which is obviously basically the length of the normal. Okay, over here. Okay, so it's not too bad. Okay, so this is how we derive it. Just before we go, I'll have a quick look in Geogebra and just show you what's happening. Okay, well, here we have Geogebra. You can see here we've got the points P and Q already plotted. Here's Q, here's P over here. Okay, now let's put the plane in. Okay, here's the plane. Okay, now the normal to the plane, where's the normal to the plane? Ah, there it is. Okay, there's the normal to the plane. Now, I'm going to create the free vector PQ, okay, which is, here we are, here's vector PQ, and let's move the normal back to basically start at P here, down here. Okay, so let's actually just move that back. Okay, yeah, let's move it back. Okay, there we are. Okay, so what we have, I'll put in R. R is actually, just to help us work out, R is actually just here. This is basically where the normal would pierce the plane here. Now what we're actually after is, if you like, the length of the projection of PQ onto the normal. The normal, obviously, you can see here is not, it doesn't even the length of the normal is actually only about 5.39 actually. And basically what we are going to do is we're going to project this vector here, PQ, into or onto the direction of the normal, coming up this way, and form a right angle triangle here, and the theta is down here. Okay. Now the length, obviously, is this distance PR. Now PR in the right angle triangle is actually PQ cos theta. Okay. The theta is down here in this corner here. Okay, so that's where the theta is. But what we have to do is, well, to get PR, which is PQ cos theta, we actually find the normal vector here, basically because if the dot, the dot product is PQ dot, say, the normal, okay, the normal here, the dot would be basically length of PQ times the length of the normal times the cosine of the angle in between. But we just want PQ cos theta, which is actually the length here. Well, sometimes you can actually think of it as like the length of the projection in the direction of the normal, I guess you could say. You could say it like that as well. Okay, so that's probably, well, that's the reason we actually normalize the vector, basically, so that the result, which will be, PR, which will be PQ cos theta, will be times by its length, which will be just 1. Okay, so that will give us that the distance d, which is actually PR here, that distance d, okay, or the distance of the point from the plane, perpendicular distance, is actually equal to PQ cos theta, okay, coming through the angle theta here in the direction of the normal. Okay. All right. Well, hopefully that sort of helps. I don't know whether that helps or not, but basically, let's actually just, I'll put in the XY plane, just the XY plane, right? This is the XY plane here. But basically, I don't know whether that helps much or not. It's probably better to take that out. Okay. Look, thank you for watching, and bye for now.